Hello. Today we are going to review the midterm review session. So let's look at the problems. Let's look at the first problem. Question 1. A small toy manufacturer produces toy castles to go with their popular line of Action Masters action figures. At final assembly, each castle is made by fitted 2 bottom pieces together and then topping with 3 top pieces. So let's mark the 2 bottom pieces and 3 top pieces. Their production process is diagrammed below. So this is the production process. Each step A, B, C, and D consists of a single machine, and the average production rates are given here. And note that the machine at step A is used to make both the top and bottom pieces, with the production rate for making each type given here. And assume that no setup time is incurred when switched between making the bottom and top pieces. So calculate the overall capacity of this system and identify the bottleneck. So by identify the bottleneck, we need to calculate the capacity for each step, and to reduce the time of the whole review session to make it compact, I just write all the solutions here, but I will explain one by one. So for step A, we can see the formula to calculate the capacity of step A is given here. However, what is the whole big thing? So we know first to calculate the mixed capacity of a mixed step. So we need to first calculate the weighted average processing time. So the 3/5 times 1/500 plus 2/5 times 1/350 is the average processing time for step A. So since we know for the top, step A can process 500 parts per hour. So for each part, the time to processing it is 1/500. And for the bottom, each hour it can process 350 parts. So for each part, the processing time is 1/350. However, we know that each castle is made by fitted 2 bottom pieces and 3 top pieces. So we know the top pieces account for 3/5 is about 60%, and so 40% for the bottom part, and this equals and so since we know the weighted average processing time, and we have the processing time in the unit of hours, so we use 1 hour divided by the average, the weighted average processing time, and then we get the 426.87 parts per hour. And moreover, since we have 426.83 parts per hour, and this includes all 5 parts, which is 3 top pieces and 2 bottom pieces. So we divide it by 2, and then we get 85.37 castle per hour. So this is the capacity for step A. And next, let's look at the capacity for step B. Since step B can only process the top pieces. So, and it can process 500 parts per hour. So 500 divided by 3, because one castle needs 3 parts, and is 166.7 castles per hour. So similar to step C, is since step C can process 200 parts per hour, and one castle needs 2 bottom pieces. So 200 divided by 2 is 100 castles per hour. And we can also see the step D, final assembly. Okay, step D. Step D is 150 castles per hour. So we know the overall capacity for the whole system is limited by step A. So step A is the bottleneck because the capacity for step A is the smallest one. Okay, so let's look at the question B. The PC Academy offers training classes for software. A course consists of 5 3-hour sessions offered as either a set of morning sessions or a set of afternoon sessions, Monday through Friday. An instructor is capable of teaching only a single course. So a single course is very important. At a time, instructors use the other part of each day preparing material and reviewing student work. There are 10 instructors. There are 4 rooms available, each of which can hold 30 students. So assuming the schedule stay the same, what is the capacity of the system? The unit is students per week. And what is the bottleneck resources? So from the problem, we know the students, we are students like the product, and we need to calculate the capacity of the system, which is how many students can be taught during the week. And the resources here are the classrooms and the teachers. So there are 4 classrooms available. So 4 rooms available in both morning and in the afternoon. So we have a total of 8 courses. 8 courses could potentially be run in 1 week. And since we have 10 instructors here, and each instructor is capable of teaching only a single course at a time, so we can staff only 8. We can staff only 8 courses. No, we can staff only 8 teachers into the 8 courses. And each course will process 3 students during the week. So the capacity is 8 courses per week times the number of students per course. Then this is the capacity, which is 200 and 240 students per week. And classroom availability is the bottleneck because there are only 8 classroom slots and 10 teachers. Remember that I said each teacher is only capable of teaching a single course. So we can simply compare the 8 classroom and 10 teachers. And we can see the classroom is the limited resource. Let's look at B. If the company starts offering classes in the evening, what is the capacity of the system? So what's different here? Originally, we have only 8 courses slots for in the morning and for in the afternoon. But now, since we start to offer classes in the evening, so we have 4 times 3 per day, which is 12 courses, could be run in a week. And what are the same here are there are only 10 teachers available. We still only have 10 teachers available. So the bottlenecks shifts from the classroom availability to the teachers. And our capacity is also 10 teachers times 1 course per teacher times 3 students per course per week. And this is 300 students per week. So for this problem, we just need to think about the teacher and classroom availability as the resource, like the machine in the manufacturer, and consider the students as the products, like in the manufacturer. Okay, let's look at question 3. The process of designing and implementing a website for commercial use can be described as follows. Okay, this is a very complicated one. First, the customer and the design team will have an informal meeting for half a day. If the first meeting is not successful, we also need to note the if. So if, that's not good. Okay. If the first meeting is not successful, then the process is over and the customer will look for another designer. If the first meeting is successful, the customer and the design team meet again for a full day. To work on the storyboard of the site. After the storyboard is completed, the site design begins, which typically takes 10 days. Immediately after that, the site is developed, which requires 2 days. So the part that I use red to highlight are the procedures of the flowchart. While the site is being designed and developed, so at the same time of these procedures, the contents are prepared, and it takes 5 days to complete. An initial draft of the contents. After the initial draft is completed, a decision is made. So a decision is made to have a marketing team review the initial draft. Experience shows that about 60% of the time a marketing review is needed. And 40% of the time, the final version of the contents is prepared without the marketing review. And the marketing review requires 3 days. And marketing review requires 3 days. And the preparation of the final version requires 4 days. Immediately after the site development and the contents are completed, the contents are then put into the site. So the contents are then put into the site. This activity is referred to as site building, which takes about 3 days. So this should be 1. After the site is built, a review activity is completed to check that all links and graphics are working correctly, which typically review activity. Which takes about 1 day. The final activity is the approval of the site, which is done in half a day. Approval of the site. About 20% of the time, the sites are not approved. When a site is rejected, it is sent back to the building activity for rework. So where's the building activity? We need to notice later when we draw the flowchart. When the site is finally approved, the design process is finished. So the problem is the first one, draw a flowchart of the process. First, we better draw a diagram like this. We denote from A to K as the activity's name, and so in the flowchart we can just use the numbers, the activity code name, instead of writing the descriptions here. And so in the diagram we have the activities name and their description and the activity times. And the activities, actually each one represents the right highlight part when we will go over the problems. And this is the description, so we know what A represents, what B represents, and the activity time are from the problems as well. So to draw the flow chart, so first we can see, since to draw the flow chart, what do we need to know? We should know the right angle. Let me use. Oops. The right angles are used to represent queues, which is like something on hold. Sorry. And the circles represents the task where values can be added, and the diamonds. No, not image. Diamonds. Represents the decisions. So at each diamond, when we need to make decision, we draw diamonds. And let's look at the flow chart. So first, we need an informal meeting with the customer, and we need to make decision whether we accept a designer or not. So if we accept it, we continue to step B is the second customer meeting, and this takes about 1 day. And next, if the customer backs out, so the 6th new designer. So at here, they need to make the decision. We use the diamond to represent the decisions. So if the second customer meeting is, so after they have the second customer meeting, okay, and they need to design the sites, which is D, and then after designing the site, they need to do the site development. After the site development, at the same time, they need to do the content preparation, which is the initial draft. After the initial draft, there's 60% of the possibility that they should be sent the draft to market review, and for the rest 40%, they don't need to send the initial draft to market review and just directly go to the final draft of the content, and the content being completed. And after the content, both the content part and the site part completed, they need to start to build the site, putting content on the site, which is the activity I. And after that, we review the site links and graphics. And then next, we the site can be approved or not. If the site is not approved, so we go back to step I to rework on the site building. So this is the flow chart. And next, let's see question B. Assume that only projects are proceed after the initial meeting are considered, and that no project will need more than one rework. Calculate the throughput time, ignore any meeting times. So let's denote Ti as the time for activity I to be completed. Since we know that after the initial meeting are considered, so which means after A, we go to B instead of being rejected. And no project will need more than 1 week, which means no project will need more than 1 rework. Which means the rework here is at least 1 time. So let's see the total time of this process. So we actually should build this. Oops. We should calculate the total time based on the flow chart. So let's see. So for step A, we need to calculate all the time on the flow chart. But how to calculate it? So it's the time for step A, the time for step B. Since there's the parallel for FGH and DEI, so we need to maximize the time for this part. No, we need to compare the time for this part and compare the time for D and E, because we need to choose the longer time, the max of these two to represent the whole time, and plus the time for I, J, K. However, because we know that no project will need more than one rework, so we know there's 20% of the chance that it will have one rework. So we plus 20% of the total time, which in here is 1 plus 20% times the time for I and J and K. And we plug in all the activity time here, so we can calculate the problem, and the final number is 18.9. So TA requires 0.5 days, and TB, the step B, requires 1 day. And the time for procedure D and E, for D is 10 days, and for E is 2 days. So together is 12. And the time for F is 5 days, and for market review is 3 days, and for the final review is 4 days. So since there's 60% of the time of the possibility that we need to do the market review, so TF plus 60% of three days is the time that market review takes, and plus this time, which equals 10.8. So we choose the bigger one, which is 12, and plus the 1.2 times step I is 3 days, 1 day, and 1/2 day, and the total number, the final number is 18.9 days. Okay, so let's look at question D. Question 4. The Urban Villa is an upscale independent hotel that caters to both business and leisure travelers. On average, 1/3 of the guests checking in each day are leisure travelers. Leisure travelers generally stay for 3.6 nights, twice as long as the average business customer. On an average day, 135 guests check into the Urban Villa. So let's look at the numbers from the problem. 1/3 of the guests checking in each day are leisure travelers. So 2/3 are the business traveler. And leisure travelers generally stay for 3.6 nights, twice as long as the average business customer. So business customer usually stays for 1.8 nights, which is 3.6 divided by 2. On an average day, 135 guests check into the urban villa. So the first problem, the first question A asks, on average, how many guests of each type are on the hotel on any given day? So if we think of the hotel as a process in the manufacture, so on any given day, how many guests of each type are on the hotel? So it's like it is asking for the working process, right? And think about working process. What can we how to calculate the working process? And we can use the Little's law, which is the Little's law is L equals R times W. So L is the average working process. R is the average throughput. W is the average flow time. So for this one, we just need to figure out the average working process for both leisure travelers and business travelers, and the rate for leisure and business travelers, and the average flow time for them. So first we can know that for leisure travelers, 1/3 of the guests checking in each day are leisure travelers, and there's 135 guests checking to the villa. So the average throughput is 100 times 1/3 is 45 guests per night. This is the R for the leisure travelers. And we know the flow time, we denote it here by the T with the subscript L for the flow time for leisure travelers, which is 3.6 nights. It's listed here. So we know we can calculate the working process denoted by I, like inventory for leisure travelers, equals R times T, which is 45 times 3.6 is 162 guests. So on any given day, there are 162 guests, leisure guests on the hotel. So for business travelers, we have 100 times the rest is 2/3, which give us 90 guests per night. This is the throughput. Okay, it should be RB. And we know that the leisure travelers generally stay for 3.6 nights twice as long as the average business customer. So in general, the business customer stays 1.8 nights, which is 3.6 divided by 2. This is the flow time of the business travelers. So the working process for the business traveler is 90 times 1.8, which is 162 guests either. After we calculate this, let's look at question B. How many times per month do the hotel turn over its inventory of guests? Assume 30 days per month. So the average total number of guests per night is 162 leisure travelers plus the number of business travelers per night, which is 324. So on any given day, we have 324 guests in total. And the turnover, how to calculate the turnover? Turnover equals R, which is the throughput, divided by I, which is the work in process. And so we can use the 135, which is on the average number check-in per day, divided by the total number working, so total number of guests stayed on any given day. And this equals 0.4167 turns per day. And we need to convert it to the turnover per month. So we use this number and times 30 days per month. Then we get 12.5 turns per month. Next, on average, business travelers pay a rate of 250 per night, while the leisure travelers pay an average rate of 210 per night. What is the average revenue the Irvine Villa receives per night per occupied room? So on average, the hotel has equal number of leisure and business travelers, 162 versus 162, and they're equal. So we can just calculate the average of 250 and 210, then we get 230. If they're not equal, suppose one is the number of people for business travelers on any day is 160. So how do we calculate it? So we need to use 160 times 250 plus 162 times 210, and divided by the total numbers of leisure travelers, of business travelers, 160 plus 162. Okay, so if they're not equal with each other, so we need to use, we need to calculate the average, the weighted average, like the weighted average. Okay, let's look at the next question, question 5. Customers arrive to the repair department of the computer store. According to a Poisson process with a mean 10 customers an hour, there are, arrival rate, 10 customers per hour. And there are 2 service desks staffed with 1 technician each. So there are 2 service providers, with each technician trained to perform every type of repair service that customers expect from the department. Assume that The service time for any given customer is an exponential distribution with a mean of 10 minutes. And we know the service time, then we can know the service rate. If incoming, 10 minutes. We should notice the units for every number. If incoming customers find that both of the servers are busy, they sit in a waiting area that is quite spacious and can accommodate a large number of customers. So this is the queue, right? And then a very confident department manager estimates that the cost is exactly $1 per minute of waiting in queue for any customer. So the cost is $1 per minute per customer, whereas the cost of keeping a service desk open is $40 per hour. So what is the utilization for the system? We know the lambda, which is the arrival rate, is 10 customer per hour. And we know the service rate is 60 divided by 10 equals 6 customer and we have two service provider servers. So the row equals lambda divided by 2 mil, and then it equals 10 divided by 2 times 6, which is 12. And this is the row, this is the utilization of the system. And we can plug in the numbers to the Excel, and it gives us the same number too. And what is the expected waiting time in queue for the customer? Also, we plug in arrival rate 10 and service rate 6 and the number of servers 2. We plug in the numbers in the Excel, and we get the queue. The wait time in the queue is 0.3788 hour. And next, what are the expected costs for customers waiting in queue per hour? So then we need to use LQ, which is the number of people in queue, right? Times the cost per customer per customer per minute times the times 60, which is 60 minutes per hour to get the expected cost. So the waiting cost per hour equals the 10 times the waiting time in the queue. 10 is the arrival rate times the waiting time in the queue, which is the LQ, the number of people in the queue, times the cost per customer per minute, which is 1, and times the number of minute per hour, which is 60, and we got 227. So this is the expected cost for customer waiting in the queue per hour. And next, let's look at the question D. What are the total costs of operating the repair department total cost equals weight cost plus server cost per hour. So since we have the weight cost, and we just need to pass the server cost. Since we know for each server desk, the cost of keeping a service desk open is $40 per hour. So the 80 here is okay. 80 here is 2 times 40. And the total cost is $307 per hour. Okay, that's the review session today. Oh, one more. Yes. Yeah. If you have any questions, so just email me and I will do my best to help you guys. Thank you. Option.